Hello, everyone. So today we're going to be expanding past the ideal gas. So far, when we've been talking about thermodynamics, we've been using the ideal gas a lot to help kind of simplify some of our thermodynamical arguments. So today we're going to try and expand a little bit past that by bringing up a new concept called the internal pressure. So, uh, if we're going to try and describe our thermodynamical functions in a non-ideal system, we're going to really need to try and back up to figure out where we've been making our approximations and how we can draw up them. So a good place to start is with our good old friend internal energy. So we know that internal energy has a dependence upon both volume and temperature. So we've got a volume and temperature dependence. And so I can go ahead and look at the change in internal energy with volume and temperature using a classic sort of multivariable calculus form, where I separate out the volume dependence and the temperature dependence. And again, I can get by with this because it turns out I have a state function. And as long as you have a state function, this relationship will end up holding. And this is going to be fairly useful. And one of the nice parts about this is when we're trying to break up our internal energy in terms of temperature and volume, it turns out we already have solved for the change in internal energy with temperature under constant volume, because it turns out this is our good old friend, the isochoric heat capacity. However, what we've been neglecting so far has been the relationship in between internal energy and volume. And so we're going to focus in on this change in internal energy with volume under isothermal conditions. So in order to try and describe this system, we're going to go ahead and start by giving it a variable. And the variable we're going to choose here is the internal pressure. And it turns out that internal pressure is really going to be a measure of the intermolecular actions holding molecules together. And we can make a certain amount of sense with this, because if I go ahead and expand my system, so if I say expand the volume of a gas, if I've got an ideal gas with no intermolecular forces, the energy isn't going to change. And whether I have to expend energy to expand a gas or whether I get energy from it is all going to depend upon my intermolecular interactions. So this is going to be inherently a measure of non-ideality. And let's go ahead and try and work this or illustrate this for an ideal gas. So we've already proven that an ideal gas has an internal energy for a monatomic gas of 3/2 RT. But you can go ahead and repeat this process for a diatomic or triatomic or nonlinear. At which point the only thing that will change will be this free factor based on how many degrees of motion we have, as long as I'm ideal. So if I'm going to go ahead and examine the change in energy under isothermal conditions, well, it turns out the only variable here is temperature. So if I keep temperature constant, well, then it turns out that my internal energy won't change at all. So this means that for any ideal system, the internal pressure is going to be equal to 0. So this really kind of helps illustrate why we've been able to make some of our simple descriptions for ideal gases so far, because any volume dependence is only going to be exhibited for a non-ideal system. And so we can use this idea of internal pressure to build up a more general description of our internal energy for any system, whether it's ideal or not, by essentially taking our internal energy is related to CV dt, and then adding in this internal pressure component for a non-ideal system. So what we see here, as we can kind of logic this out, is if my internal pressure is greater than 0, all this is telling me is that as my volume increases, so will my internal energy. And we can think about this as being due to attractive IMFs, because if my volume's increasing, it means that I'm having to add, add in energy to make this increase in volume happen. And this essentially comes because I'm breaking apart intermolecular forces. So I have a molecule or a set of molecules, and I have to put in energy to split them apart, which again is only going to be present for attractive IMFs. In comparison, as we've already seen, if my internal pressure is equal to 0, it means that I've got no IMFs because uh, it, if I increase or decrease the volume of my system, there's no change in energy, which again either means that I've got no intermolecular forces, or as we've seen before at the Boyle's temp, any attractive and repulsive intermolecular forces may just be canceling out. And then in comparison, we also have a negative internal pressure, where again, if I increase the volume of the system, the energy is going to go down. And you can imagine this happening if I have a system where I've crammed too many gas molecules into too tight of a space. And by doing this, if I ease up the volume restrictions, this means that my molecules are going to have more energy to go faster. So I would see an increase in temperature and an increase in energy. So again, this is going to indicate repulsive intermolecular forces. And we can go ahead and try and make a relation to a van der Waals gas. However, this proof does require some use of entropy, which we haven't gotten to so far. So for now, go ahead, just take my word that the internal pressure of a van der Waals gas is going to be related to the A factor, which is, again, if you may remember, the strength of IMFs for a non-ideal gas. So again, if I have attractive forces, A is positive, and so is the internal pressure. If I have repulsive forces, A is negative, and so is the internal pressure. So we see a lot of consistency in between these models. Also, one of the things I want to make note of is the reason why the term internal pressure was originally used. And this largely comes from the fact that internal pressure actually does have pressure units. But I also kind of like thinking about the attractiveness, the strength of my IMFs, whether they're attractive or repulsive, acting as a pressure or force on each other. And from that sense, hopefully you can help thinking of internal pressure is a stand-in. Also, it can be useful thinking of it again as a pressure because we see another PV sort of expression. So there's a certain similarity in between this internal pressure PV sort of energy and the ones that we've seen previously. So again, we can also look at this kind of from a more visual perspective. You can imagine I have a gas that is essentially has a lot of repulsive forces. So at which point my internal pressure is less than 0. And this means that the gas is going to naturally want to, well, repulse and expand out. And so if I have a negative internal pressure, if I decrease the volume, I'm going to essentially see a decrease in internal energy that's going to be somewhat quadratic in behavior as it eventually kind of reaches an asymptote where the gas is essentially repulsed itself away from everyone else as much as possible, and it's going to start behaving more like an ideal or a perfect gas simply because there's no the proximity of gas molecules with respect to each other is so great that there's going to be no effective interactions. And we see a very similar but kind of opposite behavior if I have a positive internal pressure, where I have gases that have found a nice equilibrium. They like hanging out with each other, and so I'm going to have to put in energy into the system in order to essentially expand my expand my chamber and break those attractive IMFs. However, the more I've expanded the system, the less those IMFs are controlling because the gases just aren't seeing each other. Until again, like with a repulsive condition, the gas molecules are so far away from each other that all interactions occur as pretty much inelastic collisions, giving me back a perfect or ideal gas. Now, one of the reasons why we like bringing up this idea of internal pressure is it really lets me expand my description of internal energy into its full three-dimensional space. Because if I have a non-ideal system, internal energy can vary with both volume and with temperature. And these relationships can essentially end up generating not just the traditional uh, isocores or isotherms that we've been describing, but will in net generate a full three-dimensional space. But one of the reasons why we love state functions is because the exact path from which I move from an initial to final state doesn't matter. And I'm able to break up any change in the internal energy into first walking down the volume coordinate, and then walking down the temperature coordinate to really capture any sort of internal energy change, no matter where I started or ended. And this is a really useful property, and one of the reasons why we've made such a push to move away from heat and more to our measures of internal energy and enthalpy. So this brings us to the end of the introduction of internal pressure. Next time, we're going to start playing around with our internal pressure equations and our new full non-ideal internal energy equation to really see what we can do with it and try and build up a better description of non-ideal systems. Until then, take care.